right, so we are being recorded. If you do not want to be seen or heard, mute and turn off your camera. And I will pass it over to Mr. Alexander to introduce our speaker of the meeting.
Thank you there, John. Yeah, so it looks like we've had a full house today. We've had Chris coming to our events now for what, 5 years or more, right? And this is actually a second talk this year, so we've done very well. Chris has basically been Mr. Database and Java for at least the last 4 or 5 years, and in London now. He's actually doing a talk for us today, or as you see, PostgreSQL for IoT. So I'm going to hand it straight over to Chris. Thanks, Chris.
Hey, yeah, okay. So this is kind of a repeat of a talk I gave at the Postgres European Conference last year, so just over a year ago now, over in Milan. I'm even wearing the t-shirt that I got. So I think most of you know me kind of already. I'm a bit of an IT jack of all trades. I don't even have a degree in IT either. And I've been using Postgres now for about 15 years, and of various points throughout my career professionally. And kind of this talk is based on a number of different IoT projects that I've worked on myself and how we've used Postgres in those situations. And obviously the fact that I'm at a lug, I'm obviously very much into open source software and even have several open source projects of my own. So when we talk about IoT, we tend to often think more about the things that are more visible, usually to consumers. So for example, smart light bulbs, smart heating thermostats, maybe smart switches, all these kind of things that are devices that you can have in your home that will connect up to some kind of platform somewhere, and either be interactive or send data. But IoT is quite a wide ecosystem with quite a lot of different things. And it's not really a case of that kind of highly visible consumer IoT space being what's all out there. There's a number of other things that kind of fit into that space. So these are just a couple of the kind of IoT projects I've worked on throughout my career. So back in the early days, I used to work on connected set-top boxes. So these were digital set-top boxes for TVs that would also connect up to the internet. And we used to do a fair amount of data collection and also command and control through that kind of platform. I also spent a number of years working on smart energy meters. So taking data off smart gas and electricity meters, aggregating that together and displaying that to users through a website. And a lot of people might not think of that as kind of IoT, but it's a device that's connected to the internet that's sending data. I also worked on connected, what are called CHP, combined heat and power engines. So these are very big, usually marine style diesel engines with a generator attached that are used to provide cheap electricity in large buildings and in industrial sites. And that kind of system was collecting 600 different data points from those engines and feeding that up into a cloud platform. And then there's my own little IoT project, which is a connected Kanban board. So often when we look at IoT systems, it's really about what we call time series data. We're collecting data that's kind of serialized in order of time. And we're interested quite often in that value, that data point at a particular point in time. So one of the big questions often when we talk about using Postgres being a very general purpose database, is why we shouldn't use a more specialized database. So there's a number of different specialized time series data stores out there, such as Influx, Prometheus, to name just a couple. And I'm kind of always a bit of against kind of these single use case solutions. They tend to focus on a very narrow area, and what's kind of interesting is often they don't actually provide significant benefit given their narrow use case and design criteria. So what's the point in having a new time series data store with its own weird and wonderful query language when we can just use the data store we're using for everything else and a much more powerful query language, usually being that SQL. So these often also have very limited data types. You can usually only store like time and then maybe a number related with it. You certainly don't get the power of, say, Postgres, where you have an extremely rich and extensible type system. And then a lot of this is all just predicated on them being highly performant for their particular use case. But what's fascinating is that actually Postgres can outperform these specialized data stores in a number of situations and scenarios. So it's not really, it's kind of actually quite impressive really that Postgres in itself, as a general purpose database that's designed to handle a complete plethora of different situations, can outperform in terms of kind of speed and efficiency these specialized solutions. So why should we use Postgres for this kind of scenario? Well, I mean, I kind of go back to my main reason I tend to keep using Postgres. So for people who don't really know Postgres very well, it's a relational database, very much like, say, MySQL, Oracle, MS SQL. It actually started off as a project in Berkeley University in California back in the mid-80s. And it was what we actually now kind of really think of as PostgreSQL, is kind of a restart of that project in 1995. So the original version of Postgres didn't actually have SQL support, SQL support. That was kind of added in Postgres 95, which then evolved into the kind of current PostgreSQL project. So it's actually got, you know, and there is bits of the code that do date all the way back to the original Postgres, called Postgres because it was post-ingress. So we've got that kind of heritage of relational databases right from really when they first came about. And it's often called the world's most advanced open source relational database, which we kind of say with just cause because it is extremely flexible, it's extremely extensible, in that there's a huge number of different extensions that you can plug into Postgres that adds different data types, add different ways to interact with data, to query data. So for example, there are extensions that add geographic information system support, so something called PostGIS. We can also actually have dedicated time series data extensions. Although this talk doesn't really focus on using any specific extensions, it's purely about how we can use out-of-the-box normal core Postgres. And one of the kind of things that Postgres has always been very good at is it's always taken safety and reliability of data as its #1 priority. So unlike, say, databases like MySQL, where certain settings can get you into some very strange situations, the Postgres has always kind of been very strict on ensuring your data is accurate and looked after correctly. And again, it comes back to really that IoT is not this really simple problem. It's not just about storing time series data. It's about the actual value of this often is being able to take that time series data and analyze it with other data. So combining data in a relational world, we call a join, right? So there's some very simple kind of questions that we might want to ask of our system. So again, these are examples that come from when I worked on smart energy data. So we've got meters and houses collecting data. We know where those houses are. So it's really easy for me to ask that system, what's the average energy consumption of Shropshire? You know, we know the number of properties in Shropshire. We know the bounds of Shropshire. We can do that kind of geographic join with Postgres. We can do that kind of arguably quite complex question that with other data systems would be extremely complex to write. You'd probably have hundreds of lines of application code. Whereas in SQL, you can do that in like 3 lines of SQL. Or, you know, what's the average energy consumption of a bed with 4 houses in the summer? You know, what's the average min-max energy consumption of a 4-bed house in summer in Shropshire? And then we can even go down to say at a half-hourly period, right? And, or you could say, what's the average energy consumption for houses within a radius of my house? You know, compare yourself to your neighbors. And these are all questions that with SQL are actually really simple to answer. So before we go on to actually how we might get the data into Postgres, we should go and have a look at where the data comes from. So this is the only time I'm going to mention Oracle in this talk, and that's the Oracle. And as she said to Neo, you must go where the path of one ends, i.e. the source. So again, these IoT systems, they tend to vary hugely from having a really small amount of computing power to actually quite a lot of computing power at the edge. So this is a panel of my own little IoT project, which actually runs on an ESP32. So we have a dual core CPU, 32-bit at something like 240 megahertz. We have a whole 500 kilobytes of RAM, and usually about 4 megabits of flash storage. And we have, a Wi-Fi and TCP/IP stack, and we have FreeRTOS. I mean, obviously, you're going to be quite limited on what you can do with that kind of power. But for my use cases, it works perfectly. So we're basically scanning an RFID card and sending that data up into a cloud platform. Another example of the complete opposite end of the spectrum. So this is a Hive hub, Hive being a smart home, smart thermostat provider in the UK. And these devices actually have fairly powerful processors. So they're a TI OMAP for those kind of hardware geeks. So they're a single core 1 gigahertz ARM chip. You've got 500 mega RAM, you've got 4 gig of flash, you've got Ethernet, Wi-Fi, you've got Zigbee, and it runs Linux. And this ran a full Linux stack. And this is complete opposite end of the spectrum to the kind of small, just more sensor orientated devices. And then we can go into the realm of a slightly more industrial setup where these devices are relatively powerful in their own right. They're 200 megahertz ARM core with 128 mega RAM, but they are there doing a very important job. They are in this instance, so this is a control panel for a CHP engine. All of these units are controlling and managing different parts of that engine. And that's a very important job that you can't stop doing. So obviously you're running a real-time OS, and it's a proper hard real-time system where actually each of these different boxes have got their own dedicated controllers managing certain aspects of the system. But in this particular setup, sending data up to a cloud platform for telemetry reasons isn't really the main priority. The main priority is managing and keeping the engine running safely. So if for some instance you can't talk to the cloud platform for a 5-minute period that you might be sending data, then that data is not getting sent. So again, this just covers a bit of a range of different systems and the actual kind of hardware capabilities we have at the edge, which all then kind of lead on to the balancing act of how we collect data. So we've got a number of factors that we want to balance off on IoT data, in that we've got the latency between that data being collected and sent up to a platform. We've got whether we can store that data locally on the devices. We've got the power consumption involved. Is it running on a battery? Is it got plenty of wall power available? Is that power available all the time? What's the bandwidth of the interconnection? Do we have a full ADSL line we can max out, or do we actually sending stuff over GPRS? What's our connectivity? What's the platform we're connecting to? And what's the cost of all this, right? It costs money to send data and to collect data. So if you don't have a business case to back it up, it's not very sensible. And really, a lot of these factors will trade off with kind of your latency requirements. So you can make sacrifices in a lot of these areas if you can sacrifice how real time you need your system to be. And this is kind of a fairly key thing throughout the talk, to be honest, in how we approach and manage data. Is all about how we trade off these different factors. So at a kind of fairly basic implementation level, we're probably talking a protocol called MQTT, which is a very lightweight message queuing protocol between these devices and the cloud. So even my little ESP32 based IoT device opens up a TCP connection running MQTT up to the platform. I've worked on platforms that try to do this with something called AMQP, which is the advanced message queuing protocol, stuff like RabbitMQ Talk. This is a really terrible idea for lots and lots of reasons, and it was extremely expensive. One of the reasons the company almost went bankrupt. And there's also been another of very strange reinventions of TCP I've seen. So, for example, an engineer designing his own reliable datagram protocol over the top of UDP because he just had some strange ideas and aversion to TCP. And then also reinventing DNS because that was a problem that needed solving again, apparently. And most likely, especially on low-end hardware, you kind of want to be sending binary data across these protocols. So the packets and payloads you can be sending, so my IoT device that I designed myself, you're talking like 100 bytes kind of when an event happens that you're sending. And especially when we get into the role of like consumer devices where data is often being collected not really for the direct benefit of the user, but maybe for additional services you want to sell or upsell to the user, or maybe to gain more insight into them to actually help optimize your system and the platform as a whole. And these kind of things then you have to be careful of things like power consumption and bandwidth. You know, obviously somebody's internet connection might have a bandwidth cap on it. And if your little thermostat is actually consuming 2 or 3 megabits a second all the time, especially in an upload or something like that, you know, especially in this current COVID era of everybody using Zoom, it's not really what people want. And the other fascinating thing is devices that operate much more in more remote environments. So gas and electricity meters are quite interesting. So they send all of the smart meters send all of their data back to the energy hubs using GPRS over the GSM networks. So GPRS, not exactly high throughput. It's also very expensive to use during the daytime. So all of these devices actually send data overnight in a batch. So these meters will they are sampling data throughout the day. So they'll be recording energy consumption half-hourly bands and then transmitting that data as a batch at the end of the day. What's also fascinating is gas meters. Gas meters aren't allowed to be powered directly by the mains, for example. So obviously electricity meter has access to an electricity supply. However, the gas meters have to be battery powered. And that meter and battery has to last for 10 years. So those devices are engineered and optimized to use the least amount of power possible. So they will only effectively wake up every 30 minutes to read the meter sample and then talk to get the electricity meter to send the data back. So we can also do fun things and smart things with, especially talking about the latency requirements we have, because we don't always have to stay in a slow mode. We can switch into a fast mode when we want. So one of the ways we can get around and trade off some of those latency issues and cost is that we can do things slowly normally, but when somebody's looking at a device or a system, we can then actually start generating data in much more real time. So some smart energy systems do this where they're normally sending data say every 5 minutes, but actually if you want a real-time view, they will start sending it every second. And again, all of this needs to be traded off with your business model and your economics of the whole situation. IoT often is what we call a hero product. So you sell one device that's got to then fund your platform for X number of years, the number of years the customer wants to keep that device. And your profit margins on that device could well be something like, say, £20. If your platform is costing £1 per month per user to run, then you're going to go bankrupt fairly quickly. And the other fun thing is actually quite difficult to authenticate devices. You know, hackers are fairly intelligent. They can actually extract things like TLS client certificates out of these devices. And it can be often very difficult for you to authenticate whether it's a legitimate device connected to your platform or somebody doing fun things. So now we've had a bit of a look as to where the data comes from and how we might get it up to our platform. This is where we start getting and talking a bit more about databases. So how do we want to store data? And this is actually kind of fairly deceptively simple. So for people who have had any experience or exposure to SQL databases, this should look fairly straightforward. We have a table with 4 columns, 2 of those columns being the primary key. So we've got some notion of a device identifier. We also have a timestamp where data was collected. And then we have the data points we're capturing. So for this particular device, it's got a temperature sensor on board and a light sensor. And we receive those readings, say, every 5 minutes or whatever our kind of interval is. And all we really need to do in this kind of very simple scenario is to just store that data on a table. And actually, Postgres especially is fairly efficient at append-only data storage. You have a table you're constantly just writing new data to. It's not really an issue. And we can start mixing things up a bit. So we might have devices that are sending data for non-regular intervals or for non-defined intervals. So Postgres in its very rich data type system has the concept of range types. So we have a specific data type called a TS range, which is a timestamp range. So we have a start time and end time, and a kind of way of bounding that. So we could, as a timestamp range, we can capture the concept of a day, a month, a week, all in the same kind of table. And we can have these overlapping kind of data measurement quantities. And this is quite useful for certain situations where your devices might be recording events that happen. So you could imagine a thermostat set point. When the user changes the temperature on the thermostat, i.e. the set point for that kind of control system, you don't need to constantly sample and record that set point all the time. You can just store when it changes, and then you store the time window. And by setting kind of the upper bound of this range to say infinite, we can have what's the current set point. So this is a really great way to, rather than having to store, say, every 30 seconds across a day, you could just store maybe 1 or 2 values. And it's also not unusual for you to have metadata associated with the data. So we might have a bunch of, this is especially true when you think about like server monitoring platforms. You might be collecting a data point, but then there might be a whole bunch of associated metadata around that data point as well. And again, Postgres is a very flexible kind of type system. We have a data type called JSONB, which allows us to store arbitrary, effectively name value pairs following the JSON spec, but also in an efficient binary stored manner. So one of the more interesting things of certain IoT systems is that we might, so I was talking earlier about that energy meters sample data every 30 minutes. And that data, so a smart meter, electricity meter, is tracking your energy consumption every 30 minutes, as well as your daily energy consumption. And that's all being sent back to the platforms on a daily basis overnight. Now, the profile half-hourly consumption of your energy doesn't really make a huge amount of sense other than in the context of a day. And it's actually quite interesting. If you see this kind of data, you can spot when people have a shower, when they put the oven on, things like that. When the hot water heater might be going, stuff like that. But you usually don't really look or analyze that data at a period of less than a day. Or, for example, on a CHP engine, you're sampling data every second, but you can't really draw a graph of one data point anyway. So you're always going to want a certain number of data points to kind of draw and visualize things. And one of the downsides to storing data in Postgres is what we call the kind of row overhead, the tuple overhead. So if we think about the very simple device that we had a device ID, we had the time it was data was sampled. And then we've got our two actual data points, which is the temperature value and the light value. So the actual binary storage space used for this kind of actual data record is 32 bytes. We've got 16 bytes for the ID, 8 bytes for the timestamp, and then 4 bytes for each of the two values we're storing. But there's a whole bunch of overhead to store that row, which is actually about 24 bytes. And this is all related to transaction control and multi-version concurrency control things, and a whole bunch of other stuff inside Postgres that we're not going to go into at all in detail. But because the data we get from IoT devices tends to be quite narrow and often can be comparable to this row overhead, effectively 50% of our table or our storage is wasted doing nothing. So if we go back to this concept of then being able to hold stuff in aggregate together, we can use the array support that Postgres has. So in storing energy metadata, we would hold the daily read, and then we'd hold the 48 half-hourly profile consumption units all in the same table. Now, the advantage of this is we're making that row much wider, and therefore the trade-off between wasting 43% of our table drops down to, say, wasting only 16% storage space for this kind of tracking of the metadata that's required. So now we've got a basic fundamental understanding of how we can store data. How do we get the data in? And this kind of, normally you just think, right, I'll just write an insert statement. Now, by default, if you're doing that, that's operating in what's called auto commit mode. So every insert statement you run will cause a transaction to commit. Now, based on the ACID guarantees of a relational database, that means that that insert record, the data is written into the table, has to be flushed to your permanent physical storage before that transaction returns to your client application. And especially if you're, say, running on spinning magnetic disks, this, what we would call commit rate, is actually really low. It can be around, say, 30 to 60 transactions a second. On modern SSDs, it's obviously a lot higher, but it's still not going to be thousands or hundreds of thousands of records a second, which is what you need to kind of be loading, and to be loading consistently, continuously. So we have to load data in batches. And again, this is where we go back to that trade-off between latency and throughput. And in order to be able to insert with a consistent high throughput, we have to trade off and sacrifice latency. And it's also important to remember that it doesn't matter whatever fancy system you put in front of this, it's a physical limitation of storage mediums, in that even the fastest SSDs around, you have still got a boundary as to how fast you can physically flush data to that disk. And actually SSDs can be quite terrible at this because of the way they write to their storage, especially multi-level cell. The commit rates for this kind of like direct flush workloads on a lot of SSDs can be quite terrible, and you need very specific ones to get decent throughputs. But by batching this data together and then putting a larger IO instruction down to the device, along with a put this into permanent storage please command, you can gain a lot more throughput. So if we have, so this kind of graph here just looks at some fairly basic loading and performance trade-offs of batching. So if we're just doing a batch of effectively a single insert, we can only really write at a rate of 300 inserts a second. So this is on a relatively fast server with decent NVMe storage. Now, if we scale up to a batch of just 10 records at a time, so we insert 10 records and then commit the transaction, we can actually at that point insert at 2,200 records a second. And again, if we scale up, so going up to a batch of just 300 records at a time means we can insert now at about 8,000 transactions a second, or in other words, 20 times faster. So, and this isn't actually particularly difficult to do programmatically. In Java, it's a case of inserting into a batch and then executing a batch. And the kind of driver deals with all the fun for you. But obviously this is still a relatively naive approach. So this is comparing different methods. So single insert, where we're getting, say, a couple of hundred records a second. Our batch insert, where we can easily get up to, say, 50,000 records a second on this particular test and scenario. And then a slightly different way of doing that batch. So we're inserting in batches, but committing a checkpoint time interval. We get a little bit more performance gain. But Postgres has another magic command called copy, where it effectively takes a stream of pre-formatted data and throws that very efficiently into a table. And using that method, we can now insert, rather at, say, 50,000 records a second, more at a point of 150, 200,000 records a second. So again, we get another 3 or 4 times speed up by using these more advanced APIs that are obviously more complicated to code with from an application level, but if you're building this kind of system, this is the kind of thing you're doing. And again, the performance of copy really ramps up very quickly. So we only need a batch size of 3,000 records to effectively hit the absolute peak limits that Postgres can write to the physical medium on this particular server. So I think this server was 8 cores, 32 gig of RAM, and NVMe storage, and you can see that we're inserting data at about between 225,000 records a second and 250,000 records a second, which is quite a lot of data points. Now, again, more Postgres tricks we can use to prevent stuff going wrong. When we're inserting these big batches, if we have one thing like a duplicate primary key, say we had 2 samples taking at the same time because a clock changed somewhere, or we have data out of order, something like that, your data quality is usually not that great. But we've got tricks that we can use to, rather than having to fail and abort that whole batch and then potentially drop down to inserting every record to find the one that didn't work, we can use tricks such as Postgres has a feature called onConflict, which allows us to specify, insert this record. If you can't insert it because it violates the primary key, then we'll update it instead, or in fact, we'll just ignore it. So these are, again, additional features of Postgres that have gone in over the years. So I think this has been in since 9.6, so it's about 5 years old at this point, 4 years old, as a feature that really help kind of actually make ingesting this data a lot easier. And again, other features of Postgres we have is the concept of an unlogged table. So an unlogged table is a table that doesn't have any durability guarantees. So rather than writing to what's called the write-ahead log or the transaction log, the data modifications that happen, an unlogged table completely skips that. And when I did this kind of benchmark, I had assumed, my initial assumption was that an unlogged table would be far faster than normal tables. However, whilst it ramps up quicker, it doesn't actually give you a huge performance overhead. And given all of the trade-offs of unlogged tables and the downsides, such as if you restart your server, that table is truncated and all your data's gone, there's very little use in using this. And obviously, these days, Moore's law is mostly now fulfilled by parallelizing servers as opposed to increasing the throughput of a single CPU core. So we can obviously take advantage of this, and Postgres is fairly good internally at being able to support multiple sessions at the same time and multiple inserts. So going back to our kind of fairly trivial batched way of inserting data and then going across 8 different jobs, loading stuff in, we can easily be loading in 60,000+ records a second. Now, one of the other fascinating things about IoT as a kind of problem domain is usually the devices are running all the time, and it's a problem domain where everything is always firing data at you and it never stops, which means you can't really ever stop loading it. And again, in systems where you have multi-database servers and you're replicating between them, due to inherent limitations of how that replication works, that can impact how fast you can replicate data. And what you always have to make sure of is that you're not pushing data in faster than you can actually effectively physically store it. So your speed that you can load data into a multi-clustered situation is effectively as fast as you can push that data to the kind of backup and secondary node. And the other thing that's kind of makes life fun in this particular situation is you don't really ever get a maintenance window, because you don't ever get downtime. The devices are always sending you data. You have to be careful about how you schedule backups. They can't put too much load on the server. Your maintenance jobs need a lot more planning, right? You can't just go and turn the server off now and do some maintenance. You have to fail things over. You have to move work around. You have to spread the load out. You potentially have to buffer it in memory somewhere or to disk, which makes all of this kind of what you would consider normal routine maintenance of managing systems actually quite a lot more complicated in this kind of environment. You can't just go and apply your server patches and reboot on a kind of weekly schedule type thing like you might in other situations. So when things go wrong, one of the fun things with these IoT platforms is they're effectively huge distributed systems where you've, say, got 1 million devices in the field split around the internet. In many regards, that looks like a distributed denial of service attack. And if your firmware engineers cock things up, that's exactly what happens. So there was an outage a few years back that was effectively caused by, it was triggered by the kind of communication server that's handling all the traffic from these devices into the platform falling over for about an hour. This kind of relatively minor outage actually caused a 3 or 4 day long outage because all of the devices got a disconnect at effectively the same time. And all of these devices were designed to, after 30 seconds, reconnect. And so obviously you get a thundering herd style problem here where you have thousands of devices in the field all trying to connect to you and send you data at exactly the same moment in time. And you end up in this complete congestive collapse and failure mode where basically the only way to get the system back online is either to massively ramp up your platform capacity or to tell people to turn things off for a while and to randomize startup times and stuff like that. So as somebody who works on these platforms or architects these platforms, you need to make sure that your firmware engineers don't do dumb shit. You need to make sure that any kind of reconnect timers they have, or even sampling timers they have, are skewed and randomized. Now, this is more about like when you transmit data as opposed to when you collect data. If you need data to be collected exactly at wall time, so for example, if you need data to be collected on the hour and like say every 5 minutes at intervals, but actually at 5 past, 10 past, quarter past, etc., you can sample at that point, but don't transmit it at that point exactly. Skew that time window so that you don't have all your devices sending you data at exactly the same time, which then just puts you then have a very, very peaky server load where every 5 minutes you get thousands of requests come in, and then you've got 4.5 minutes where nothing happens. And all these kind of things, you have to think about the system as a whole. And even if you're just working down the database level, how people send you data has a massive impact on the load pattern of that server. And again, all of the technologies in between collecting that data and ingesting into your database, you need to be kind of thinking about how you deal with these situations. And it's especially true of especially batch systems. Can you load a day's batch of data faster than 24 hours? Because if you can't load data faster than 24 hours and you miss a day for some reason, you can never catch up. So you always need to make sure that you've planned to have a level of headroom in your loading system and your database system so that you can't be running at the absolute limits all the time. So now we've got a lot of data into our database. How do we go about managing that data? So like the smart energy database I worked on was 5 terabytes of data. These you know, and these other kind of platforms are non-trivial amounts of data that you're storing, and often needing to store and manage for long periods of time. It might be that you want to store that for multi-year periods. And you know, thankfully, hardware has got faster and more dense in the speed and data densities that we now have with modern storage devices and modern memory is really quite incredible. But we can't really just keep on throwing everything into one table. So this is where we can start using more features of Postgres called partitioning. So partitioning, most IoT data will partition either on, say, a dimension such as time quite often, right? So for example, we might have Monday's data, Tuesday's data, Wednesday's data, Thursday's data. Or we might be able to partition on, say, region or tenant or something like that. But there are many ways we could handle this kind of data load. For example, we could do something silly like have a data table for every single device we have. And Postgres will quite happily handle 800,000 tables. Your backup system probably won't. And, or, you know, there's other silly approaches people have done, such as let's have a database per tenant, so per kind of customer we have. Have you ever tried to do a schema change across 600 databases at the same time? It's not easy and it's not fun to do. So partitioning gives us a really great way around this. And especially as Postgres these days has all of this declarative partitioning built in. So if we go back to our original kind of table, we're going to make one very subtle minor modification to its definition. So we're going to tell Postgres to partition this table by range. So all we're telling here is Postgres that what we're going to do is we're going to partition this data set by the range of the values on the column read at, which is our timestamp. So this is just fairly basic time partitioning. And then we create a bunch of tables that are the partitions that we attach into this partition table. So we can specify the from and to values of that range that we're going to store into an individual table. Now in this exact example here, right, we're storing data we're partitioning by month, roughly, I think. So we're storing, for example, we have a table for the October 2019, we have a table for February 2020 in this particular example, and obviously bits in the middle. Now, this also gives us the ability to manage that data once we decide we want to get rid of old data from our system. So rather than having to do expensive deletes from a system, we can just get rid of an entire bucket of data. We can get rid of that entire table. So again, these are all really great features that exist in Postgres for a whole bunch of different reasons, mainly for like data analysis workloads, but make really useful sense for our particular problem domain. And if we're going back to our kind of loading performance, partitioning has a bit of an impact because every insert into that main table has to be routed down to the actual partition. So we lose about 17% to 34% in our different loading scenarios and situations. But given the advantage it gets of us managing data, it's not really it's a sacrifice worth taking. So we can also do fun stuff, such as at the point we want to get rid of data, we can detach that partition from the table so it's no longer queryable. And then we can potentially archive it off to a file in this instance, and then delete that table. Or we can do other fun stuff with table spaces. So often old data isn't queried very often. So rather than keeping it on our fast, super expensive storage devices, we can put it onto big, cheap storage devices. So for example, our server might have a nice fast RAID array of NVMe storage, and then it might have another array of either network attached storage or big spinning disks that we can use as an archive, and we can push that data. We can basically move that partition from our fast storage to our slow storage at a point where it's not used as often. And this allows us to balance and manage all those kind of cost trade-offs with how often this data is actually queried. So again, other fun features of Postgres. So one of the other very cool things with Postgres is it has a completely pluggable index system. So most databases only really use an index type called a B tree, binary tree. So a very classic way of indexing data where we store effectively a complete binary tree of min max values, and it's all ordered. These indexes are obviously great for speed and performance, but take a huge amount of time to build and also a lot of storage space to store. And because Postgres has this long history of being able to have new interesting index types created quite easily and loaded as extensions, there was an index type that came up mainly for dealing with very large analytics data called a BRIN index, or a block range index. So this index is about tracking the minimum and maximum values of records stored on a database page. So data stored in Postgres will be stored into blocks of 8 kilobytes. And this index basically looks at what's the greatest value for a particular column in that storage block and what's the minimum value. And we store that much more simple compressed data. Now, this only makes any sense for workloads where there is a correlation between when you load data and the order you want to look at your data in, which is really great for IT data because it's often time series and we're often loading it in the order it's generated. So basically at the top of the table will be the oldest data and at the bottom of the table will be the newest data. So this index method then works really well. And you can take, say, a 30 gigabyte index down to a couple of megabytes. There are some trade-offs in that we lose the ability to do things like unique matches. So we can't really use it for primary keys, but we can use it for, say, history tables. So this is a quick example here. We have a table that's going to keep our history of all our readings. So this is kind of like more archived data. And what we're going to do is just create an index on it using BRIN on the column read at. So we'll have a time ordered index. The data in that table is inserted by time. So there's a correlation between the actual physical storage on disk and the data logically. And so rather than to do this with this table, if we wanted to query the data, obviously, if we had no indexes, we'd have to do what's called a sequential scan. So we'd have to read through every single block of data stored on that table. And that, in this instance, across 23 million rows, took 1.3 seconds. Now with that BRIN, and this is obviously looking for a specific day for a time period. Now with that very simple BRIN index, it took instead 140 milliseconds. So by adding this index type, we've gained a factor of 10 speed up. Obviously, compared to a B2 index, it's 100 times slower. So we're taking trade-offs here, but that's all traded off with the fact that a B2 index is 800 megabytes versus the BRIN index being 800 kilobytes. So we've used 10,000 times less storage space to accelerate the query 100 times. And if we have a look, the sizes here, the actual table size is 1.3 gigabytes and the actual index size is 800, 900 megabytes. So this isn't uncommon for this kind of very narrow IoT data where effectively the B2 index size is almost the same size as the actual table and the actual store record of all those rows. So these kind of techniques have got me out of trouble in the past when we had a bunch of tables that we'd load data into before we process and move them to the rest of the system. And we were getting quite close to running out of disk space on our production system at that point in time. The indexes, the B2 indexes on all of these kind of staging tables was 300 gig. And again, because of how we used them, we only really used like the latest data, and we only ever really looked by time. We weren't looking for a particular value. So we swapped these indexes out from B3 to BRIN, and we went from 300 gigabytes to 2 megabytes, which got us an awful lot of storage space back. Again, these indexes are also really good for things like audit logs and that rarely accessed data where you don't care too much about time, but you want something a bit quicker than 1.5 seconds to query. So now we kind of had a look at storing data, loading data, managing that data. How do we actually get answers out of all this? We've done a lot of work to get data in, but we actually now want to answer some questions. So if we go back to those initial questions that I kind of postured at the start, what's the average energy consumption for properties within a particular location? So for people who don't know, this is the postcode of Shire Hall in Shropshire, in Shrewsbury. And what we're going to do is we're going to look at all the properties around there within a distance of 2,000 meters. So this is a good example of being able to use additional extensions in Postgres to be able to do a spatial, so geospatial join. So what we're actually doing is looking at all of the postcodes within a certain location. So we're going to find all of the readings nearby within a 2,000 meter circle effectively. And then we're going to consumption and min-max consumption. Now this is a question that if you were to code an application tier on one of these dedicated time series databases and the other systems you have to join data with to do this kind of query, it would take you hundreds and thousands of lines of code, application code to do that, whereas you can do it very simply in SQL and Postgres with one query. And again, so this is a case where what's the average consumption for properties with 4 bedrooms? Again, in SQL, this is just a join. It's all really trivial now. I'm filtering by dates. So as we start getting more advanced SQL, we then want to be talking more about how do we start presenting that data. So quite often we want to present data in time buckets. So data might have been collected at various points in time because we've skewed all the sampling windows, but we want to kind of align them to say 5-minute, 10-minute regular intervals. And again, using pure built-in functions in Postgres and a bit of SQL, we can do all this pretty easily. So Postgres has a really nice function called generate series, which will just generate you a series of timestamps at a regular interval. So here in this example, we're generating 10-minute time intervals across a day. And then we're going to join that with our actual reading data and organize all of those readings into those buckets. And then it's very simple just to aggregate it. We can even keep all of the real data points. We can pick the average, the kind of actual aggregation you do to get that value will be based on your data a little bit. For say, a lot of stuff mean is usually acceptable. So this is just actually relatively straightforward SQL that's actually doing a fairly complex task. And we can go on to even more advanced SQL. So a feature in Postgres that's also available in databases such as MS SQL and Oracle is called window functions. Window functions are aggregates. So they're a way of looking at and aggregating a set of rows together to produce one output, but in a way of effectively sliding a window down your result set. So you have a list of data points. A window function lets you look at, say, 5 at a time or something like that. So we can use these to do very cool things, especially this was especially useful for energy data, whereby we're looking at often counters. So your electricity meter is tracking your energy consumption by recording a counter that only ever goes up and is completely hardware non-resettable. But that means to work out your actual energy consumed in any time period, we need to know the previous value to be able to take the difference. So we have to have effectively the current value and the previous value to be able to actually work out how much energy you consumed during that time period. So in this instance, we have a table of meter readings of each reading ordered by day. And we're going to use this window function called lag, which, as you might think, gets you the previous value or the previous record. And we're going to do that over a window of everything but ordered by the day value. So we will always get the previous value. And then it's a case of just subtracting that from the current value to get how much you consumed. So again, this is quite a fairly complex logic that you have to do in an application level that you can do very simply in SQL. And we can go and expand this further by saying, okay, now I've got my daily consumption. Well, let me have the weekly consumption as well. So we can do things like we have a window function and we're going to sum that data. So we're going to add that data together in that window. And that window is a case of partitioning that data by the week boundaries. And again, that's a very simple line of SQL that allows us to do this. And we can go even further. So Postgres has got some very advanced window function support. So we can specify like ranges of rows to look at. So this is like really good if you want to calculate, say, a moving average. So this particular example is going to calculate a moving average of your energy consumption, which would then be useful for doing some basic trend analysis to say, is my current consumption today higher or lower than, say, the rolling average of the last week? And this is all like analysis you can do, again, really trivially with a few lines of SQL that in other systems would take you days of engineering time to develop. And we can go really super advanced here. And how do we deal with gaps? Because your IoT data is going to have gaps. And a bit like the tube, you want to mine those gaps. So this query looks fairly complicated, and to a large extent it is. And essentially what it's doing is, again, based off of that energy reading example, we are going to interpolate missing days, because it's always an ever increasing counter. So if we know this value and this value, we can then generate the ones in the middle in a linear approximation. Now we have to pull some tricks in Postgres to be able to do this. Firstly, we actually have to define and create our own aggregate. So Postgres allows you to create any aggregate you can think of using a fairly straightforward function and then just a definition of these. And they basically work by, they have a function that has a state and then sees the current variable, and you can do whatever you want. And for this particular, what we're going to do here is all we want to do is hold the last known value. So we have an aggregate we created called last, and its definition as a SQL function is super simple. We're just going to hold on to whatever the last value we had was. So to start building or understanding this query, we've gone and got our date ranges we want to look at. We've gone and joined that. We've gone and joined that to the actual data we've got. And then we can go and use this aggregate function we created to go and look back and look forward. So for every row, we can go and look at the last value we had and the next value we had, and we're going to take the energy data and the date and the time. So then we can interpolate it very simply by what's the min read, the max read, so what's the difference across that, how many days does it span? So just divide it to get the average per day and then multiply it by my position. So a very complicated query, but actually answering a very complicated, powerful situation. So as a bit of a note, again, everything I've kind of talked about here is how do we deal with just doing this in stock Postgres. And there's an extension called Timescale, which is basically a dedicated time series data extension for Postgres. It's open source. Bits of it are also dual licensed commercially. So, but the core extension that gets you a lot of very cool features is completely open source. And they have much simpler ways of doing that gap filling that I just showed you, using some fairly straightforward functions they've designed. We've also got cool things such as doing continuous views where you can be rolling up and building roll-up aggregates in real time. And it's a very cool extension and well worth looking at if you're actually playing with any time series data. And one of the cool things here is, and this is where I find it quite cool, that Postgres, and even these stats were actually taken from the original version of Timescale where they hadn't really optimized anything. but for the same resources compared to Cassandra database, Postgres and TimescaleDB was 5.5 times faster at using 10% less resources, which is, I think, quite impressive. And since I wrote this slide, TimescaleDB have optimized stuff really substantially now that its performance gain across just stock Postgres and the dedicated time series databases is really quite impressive. So thank you for letting me bore you all. And does anybody have any questions? So I don't know if Mick wants to explain his question because I don't fully understand it.
What are you working on at the moment, Chris?
What am I working on at the moment? Home insurance. Something completely different. Yeah, I've been building out very simple home insurance journeys for a division of GoCompare. So nothing quite as interesting for the last few months.
Hello there, Chris. I think Mick probably means that if you're interpolating values, how do you tell which values are real, as in like actual values, and those are which have been generated by interpolation?
So ultimately, you can always go and look at. So what you'd probably do is have another column that just marked whether you had a value there or whether it had to be interpolated. So obviously, if you don't have an underlying value, it would say null. Then you could easily just work out that it's been interpolated. Probably the easiest way to do it.
Somebody looking at the data provided by the database, I just wondered how they would know whether a piece of data was interpolated or whether it was an actual piece of data, whether there was any way to highlight that in the SQL, or whether you would have to code that into your front end, or what you would have to do.
Yeah, so I mean, again, there are kind of cool things you can do with Postgres. Is very flexible data types, but most front ends probably find it easier to consume that kind of metadata as a separate column, and it's fairly straightforward to just have another bit of logic based off the underlying data to say whether it is interpolated or real or actual.
Okay.
So like the energy stuff I worked on, we had some fairly complex queries like that, doing gap analysis and interpolation, and we even used to have to span stuff across multiple days. So dealing with, we had certain meters would track local time rather than UTC time. So on the kind of switchover dates in March and October, we would get days with say 46 samples and days with 52 samples and stuff like that. And we would then, on those kind of time periods, have to go and look at multiple rows in the database to build the actual real picture of the range of usage and stuff like that. So again, we used all these kind of like window function tricks to do that.
Okay. I just wondered also, because I said, would you have to declare the values? I just wondered where data is being interpolated, would you have to declare that to the end user so that they didn't think it was a real value? Would that just depend on the usage of the data they were looking at?
Yeah, it depends on your actual use case. I mean, so the kind of energy stuff we worked on, it was never for billing. It was purely for providing a website for users to look at their kind of detailed consumption and to get more value out of the smart meter, basically. The actual billing data only ever use the kind of daily read value, and they have a lot more regulated rules around how they process that and how they build the bill. So I was always quite thankful we never dealt with that, because again, it was heavy. You know, even the format of your bill is heavily regulated in the energy system, in the energy market. But yeah,
cool. Thank you.
Obviously, they do have to denote all of that, whether it's an estimated reading. So if you're on old-fashioned pre-smart meters, where obviously they can't get these kind of much more accurate readings reliably, then typically, I mean, we looked at users who on the kind of pre-smart meters would typically only have one read that was actually real in the 2-year period. So there's an awful lot of estimation that goes on by the energy suppliers, and no matter how much people might dislike smart meters, they're actually quite good for getting accurate bills.
Cool, thank you.
And the other interesting thing is how much data they track as well, because they can actually they've got very inaccurate sampling chips on them, and they can track things like reactive power and apparent power versus normal power because they can look at the actual current and voltage waveforms. And not that we ever did anything with that data, but we actually had access to all that data. Very interesting. Any more questions from anybody?
Chris, Steve here. Thanks, first of all, actually, for a really good, entertaining talk. I was following you all the way up to the point, to the section where you got to processing data.
Right.
And then when you started the the SQL queries and things like that, that's when it started to get just that little bit. For me, it was just a bit hairy. So thanks for the talk. That's really handy. Your examples and experience are obviously clearly from the time with the the smart meters and the energy company and things like that. For someone who was just doing something much more trivial in terms of around maybe in the home and doing where sensor readings are not in probably in the millions of sort of transactions and fields and that type of stuff.
Yep.
I know you said PostgreSQL is very flexible. How suitable is it in that sort of environment? And would you need to use half the tricks and techniques that you've talked about today in that type of environment? How would it work in a much more scaled down area?
Sure. So I mean, to be honest, even if we're running Postgres on a Raspberry Pi with a just a £5 SD card, you probably wouldn't have any issue loading in just with the most simplest approach of just insert a record every time you sample stuff from a couple of, you probably easily handle 10, 15 devices, sampling data every second without too much of a sweat, even with a couple of gig of RAM or something like that, or even less, to be honest. Those kind of basic stuff doesn't really take a huge amount, especially if you're just storing it. Say, like a simple weather station or something like that, you easily do. And then again, the querying is fairly straightforward, really. And a lot of those fancy tricks you don't really need to be doing unless you want to answer a complex question, right? If you just want to have a look at the data, then it's just a simple select star from, order by time. So yeah, I mean, go back to, but then that's is what kind of makes it kind of cool, is you can start off with Postgres in that kind of relatively simple way, but you can take it all the way to a production system handling 4 million meters if you want, with a bit of more engineering.
Yeah, no, it's just interesting because I think we've all played with databases, in the past type of thing, and I guess it's where's that sort of trade-off? It's sort of using my SQLite or even a Maria database to post.
To be fair, SQLite these days is actually very feature rich, and one of the interesting things is they kind of use Postgres as the benchmark and like the way to do things a little bit. So a lot of the features that SQLite has, they are mirrored on how Postgres implements them quite or defines them quite often. So I think things like window functions SQLite has. So there's no reason for small scale use you can't use that and still be using some of these SQL techniques. I mean, I mean, like other ways of doing things would be something like, if it's because quite often what gets used for, say, in like say server monitoring, say something like Cacti that uses RID under the hood, and that's very good if you want a very known, predictable small file size, but it's actually not hugely efficient at writing data quite often, and it loses a lot of precision because it tends to store like time derivatives so it tends to store rates as opposed to the actual real values. Whereas these days on modern systems, something like SQLite, not a bad option.
Yeah, that's great. Thanks for that. It's just very interesting talk. Thanks.
I was going to say, Steve, one advantage of batching or somehow caching those the processing into your database, right? Over the fact of just performance, is the number of writes you're doing to your backing store, your flash in this case. So obviously the less writes you actually do, I mean, obviously you're still storing the same amount of data, right? Then yeah, the write endurance of your storage will be increased effectively, you know, because you're not doing as many writes, and when you are, you're just doing bigger ones. And you've got plenty of memory, right, to actually support all that anyway, even on a small Raspberry Pi. I'm sure Chris probably agree.
Yeah, totally. I mean, obviously you've got a trade-off there with how much do you care about the data in event of power loss, right? I mean, so some of the systems I've got, I use another system called Hazelcast to do effectively cross-node shared memory. So you buffer data into memory pooled across a number of servers, and then write from that into the database, so you can handle those kind of situations. But obviously for small, simple use cases, then yeah, store stuff in memory for the time period that you want, and then just write it, say, every couple of minutes or whatever into your database.
Yeah, what I've done in the past actually was I stopped using SQLite, not because of any particular reason or its functionality. It was just the fact that it was on the it only works really locally on your devices, and so it was hammering the SD card on the Raspberry Pi. So I actually moved to a Maria database, you know, off the actual Raspberry.
Yep.
So the database was held elsewhere on better storage, and then I actually used that to centralize all the sort of like functions that or services that needed some database activities. Yeah, so yeah, no, I get the point about batching up and things like that, but I've moved away from that just purely for the hits on the SD card anyway.
Yeah. I mean, to be honest, on a modern, like if you've even just a cheap SATA SSD, you can have on the USB 3 on the Raspberry Pi. You won't, on small scale use, you won't really hit that kind of like commit limit.
Yeah, exactly right. But I'm trying to keep my Raspberry Pi as minimal as possible, and not have to plug stuff in and things like that. So yeah, and plus, you know, centralizing the database, I can then actually, you know, store lots of things. You know, not just the you know, one application in that one database.
Yeah, I mean, the other thing is if you are writing to the SD card a lot, it's well worth getting an endurance optimized one or an industrial grade one.
Yeah.
The CHP project I worked on, they wrote all of the stored data to an SD card on the device, and without buying kind of industrial high endurance grade SD cards, they were just burning through them in a matter of months.
Yeah. I suffered the same fate on two SD cards myself. So that's why I moved it off the SD cards and onto more physical storage elsewhere.
Yeah.
No, that's good. Yeah. Understood.
I must admit that unless I've seen high endurance storage, then for a lot of applications, people are storing sort of every second or doing a transaction every few seconds, that or logging even, you know, conventional logging on their Raspberry Pis, that they don't last more than 12 months. So it's actually quite hard on them to store that kind of data.
Yeah, I mean, ultimately it goes down to the mechanics of how flash memory works, right? And usually if you're writing, say, less than 32 meg chunks, you're going to not be able to efficiently write to the flash, and you've got, what, 10,000 writes limit of a flash transistor, right? It's just physics at the end of the day. And sadly, no IT magic fixes the laws of physics, no matter how much.
Okay, any more questions? Sorry there, Chris. Any more questions?
All right, with that, I'm going to go ahead and stop the recording. So feel free to say and do what you want.